purpose of this video is to help you out with the math that's involved with the Standing Wave Lab. So this is what your answer sheet's going to look like, and we're starting out with question 1. You're actually given this value. This is the value of mu, which is the linear density. That's a Greek letter mu right there, and that's 0.01 kilograms per meter, so that's all you'll put there. To get the mass of the string, it's simply the mu multiplied by the length of the string. So you see you've got kilograms per meter here, and that would be 0.01 kilograms for 1 meter. So you multiply it by 2, that gives you 0.02 kilograms for 2 meters. Now the rest of this I've got over here, and I'm going to show you how you can put in each of these bits of data. Now this was the data that you collected during the lab, and obviously I'm expecting that you will have collected all of this data here and not just the data that I've listed, and so you'll have all of these filled in by the time you're looking at this video. Now I wanted to show you how you can get these values here. This is for the wavelength. This is lambda, and it's going to be simply 2 times the distance to the first node. So let me kind of explain that. When you're looking at a harmonic system, let's look at this one here for n equals 3. An entire wave starts here and finishes here. That's the entire wave. And so that is effectively the wavelength right here. As you can see, the distance to the first node is halfway there. So to get the wavelength, or the length of the entire wave, we take whatever distance we see here and we simply multiply that by 2. And that works for all of these. So you can see it works here as well. That's half, and this is the entire wave here. Obviously for this one we're only seeing half the wave. But that's how we're going to get those wavelengths, just simply multiplying the distance to the first node by 2. So those values will all go in here, and I have calculated the first the lambda 2 and the lambda 3 here based upon the distances that were found during the lab, and you'll do the same thing up here. It's not too difficult. The next thing you need to do is find the velocity of the wave. Now they've got the velocity here in meters. It really should be meters per second because that's the unit for velocity. And the way that's found is to take the frequency and multiply it by the wavelength. Now the frequencies are up here, and the wavelengths are what you just calculated a second ago. So in order to get those frequencies, what you do is you take 2.5, multiply it by 4, 5.0, multiply it by 1.84, and then so on and so forth throughout each of those calculations. So you can see that I've done a couple of sample calculations there on how you get V1 and then V2, and you can continue on and get the rest of them for all the other values. The last part here involves actually calculating a theoretical frequency. Now these frequencies were found by experiment, but you can actually calculate the frequency that you expect to see as long as you've got enough information. Now the information we need is all given to us all in the problem, and here's the equation that we're using. Now really all you're changing here, at least for the first part, you put in the mass, and the mass goes in here where the MW is. The G is 9.81, the mu is 0.01, and neither of those things are going to change. You've got the N value, which matches whatever you've got next to the frequency, F1, F2, F3, F4, F5. And then that value N is what changes. So that goes for 1 here, it'll be 2, and then it'll be 3, and everything else is going to stay the same. So really all you're doing is you're taking this F1 value, you multiply it by 2, the next one you multiply it by 3, the next one multiply it by 4 and 5. So it's not really that bad. Not nearly as bad as it looks. The 2 and the L here don't change either. That's the 2, which is a constant, and the 2.00 meters is the length of the string, and that's not changing either. So it's not too bad as long as you've got the right mass in here. You've got 0.100 for all of those, and then you're just changing the value of N, which is on top of this line here. Then of course we change the mass to 0.200, and we repeat the process, and then 0.600, and we repeat the process again. And what you'll see is a relationship between these frequencies and the frequencies that you found by experiment over here, and I'm hoping you'll be able to see that relationship fairly easily. You might even be able to see it now. A couple of the other questions that you're going to answer as we go through this. It asks you for again this relationship that we just talked about. It also asks for the relationship between the value of the wave speed and the mass hanging from the string. So what you do is you go back to this table up here that has the wave speeds and the masses, and what you do is you compare these wave speeds for each of these different masses and see if there's a relationship. Is it increasing? Is it decreasing? Is it the same? And then you can always use the background here, especially towards the end in this last couple of paragraphs, gives you some good clues as to why these relationships might exist. The other thing that's being asked here is it says describe the relationship between the wave speed and the harmonic number for a fixed hanging mass. So what they're asking you to do is, for this one here that's got the wave speed, start say at 0.100 and look and see what happens to the velocities as the harmonic number there, as the harmonic number changes. So just go through and compare those values, see if they're increasing, decreasing, or if they're the same, and then again see if you can come up with a reason for that as well. The rest of it you can get pretty much just by reading the last part there of the background, or maybe even some of the beginning parts as well, but it shouldn't be too bad for you from that point. Alright, that's it.